Good day, everybody, and yet again we're back. So we want to look at a question on chemical equilibrium, and obviously we are still working hard, preparing for those exams coming up. So we keep making sure that we still become your plug when it comes to good content. So if you haven't subscribed, please make sure that you join us and become part of the larger family. Right, and I see that we've actually surpassed the 12,000 mark, and thank you so much to all of you who just keep making our family grow. And thank you for the good and kind comments. Some of you promised to buy me a Maybach. Please, you better make sure you do right on those promises. And by the way, for those of you who need help, with tutoring, please just make sure that you can just send me an email. That's info@mlungisinkosi.co.za, and we can make sure that we plug you. Whether you want help in maths or in physical science, whatever curriculum, by the way, we are able to offer you the help that you need. Okay, so I'm going to take this question quickly on chemical equilibrium. So they give us pure hydrogen iodide gas, okay, of concentration 1 mole per cubic decimeter in a sealed 500 cubic centimeter container at temperature T. Okay, so that's the information we're given. And they say the reaction reaches equilibrium according to the following balanced equation. So there it is. That's our reactant there, and it forms those two products. Okay, so that's a typical decomposition reaction. Okay, so they say to us the graph below shows how the concentration of the reactants and products vary with time. Okay. Oh, actually, I skipped something. They said define the term chemical equilibrium. Remember? So, how we define chemical equilibrium, we say this is when the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, please remember to state its rate. Okay, so we say this is when the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, right. So in this case, they say the graph below shows how the concentration of the reactants and products vary with time, okay, during the reaction. Now, I want you to notice, so in this graph, before we even get to the questions, we're looking at concentration, right, against time. So in this case, what do you start with? At 0 time, what did we start with? It must be the reactant. Remember, you haven't formed any product at the moment that is at the beginning of the reaction. So in this case, this graph here must tell me this one that's descending. Okay, so it must be the graph that has to do with the concentration of your reactant and what happens over time. You start out with a large amount, and as you keep using your reactant, it decreases, right? Okay, and what about this graph here? It shows me one of my products. So in this case, it's one of my products, and the products keep increasing as the forward reaction keeps taking place. So as a result, that's for the forward reaction, okay, or that's for your products. Okay, so let's answer the questions that follow. So they say which one of the curves, X or Y, represents the changes in the concentration of the products. Okay, so we've already done that, right? And which one shows us the product? It must be graph X. Okay, so in 6.2.1, so we're going to say this must be X. And why is that the case? Obviously because at time 0, okay, there was no product that was formed. Okay, we started with nothing. Okay, that would be one of the reasons. Or in this case, you can just simply state that as time progresses, it's the products that are going to increase in concentration. Okay, right. And then they say, how does the rate of the forward reaction compare to that of the reverse reaction at T is equals to 4 minutes. Okay, so when we get to that point there, remember, this is when the the forward reaction is still taking place quite vigorously. Remember, now when those concentration get to a point where they actually kind of when the curve flattens, okay, that simply tells us this is when we reach a state of dynamic equilibrium or chemical equilibrium, right? And the amounts stay the same because the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so in this case we reach equilibrium at that 6th minute there. But before we reach that equilibrium, it means that the rate of the forward reaction must have been higher than the rate of the reverse reaction. And why do we say that? Because it means, remember, right from the beginning, you start with the forward reaction taking place. The reverse reaction only starts, kicking in, at a later stage, once the products are formed, right? So in this case, your reverse reaction is going to take place slowly at the beginning, and that's because you've got very minimal products that are actually formed, right? So in this case, we know that at the 4th minute, so we know that the rate of the forward reaction must be higher than the rate of the reverse reaction. So we're going to actually choose higher than. Okay, right. And then let's go to the very last question. This was a very short one. So they say the equilibrium constant Kc for the reaction is 0.04, okay, at temperature T. Now they want us to calculate the number of moles of iodine present at T is equals to 6. Now remember, they are trying to say calculate the number of moles present at equilibrium, because after that T is equals to 6 seconds, we reach equilibrium. All right, so how are we going to do that? So we're going to draw our, rice table, ice table, whatever you want to call it. Okay, so I'm just going to do that quickly there. Okay, by the way, I know that most of us are used to having this table in terms of number of moles, but I also want you to know that you can also have this table in terms of concentration. So what I'm going to do is that I'm going to stick to the convention and use number of moles. So we know we have initial. Please remember, ladies and gents, that just put in those SI units there so that I know it's in moles. Okay, so that's going to be the change, and that's also in moles. That's going to be equilibrium moles. So in this case, I also have equilibrium concentration, okay, and that's in moles per cubic decimeters. Okay, sorry about that. Okay, so now I know I've got 2HI, okay, right, and I know some of you prefer to have that the ratios, you have a separate row for ratios. Nothing wrong with that, you can do that. I just prefer to just write it like that. So that's H2, sorry, and that's I2 over there. Okay, so that's H2 and I2. Okay, maybe let's write that out in a better way. Okay, so that's H2 and I2. Now, what do I have? At the beginning, I started with pure hydrogen iodide of concentration 1 mole per cubic decimeter. So it's not in the units that we prefer, right? We wanted it in moles, but we know we can convert it, right? We know that concentration is number of moles over volume. So number of moles would be concentration times volume. So in this case, our concentration is 1 multiplied by the volume. Our volume was 500 cubic centimeters. But remember, when we use this formula here, we need to convert it into cubic decimeters, right? Cubic decimeters. And how do we do that? We divide that by 1,000. So I'm going to say 500 divided by 1,000. That will give us 0.5. Okay, sorry that I'm not going to write everything out, detail by detail. I hope that you'll be able to follow on. Right, so it means that the number of moles that we started with is actually 0.5 moles. So that's what we have. That's our reactant at the beginning. We started with 0.5. And then, by the way, when it comes to our products, what do we have at the beginning? Well, of course, we said we started with nothing, right? Because they said they sealed the reactant in an empty container, okay? And our graph suggests exactly that you started with nothing in terms of the product at the beginning. So in this case, we always are given something at the beginning and they give us something at equilibrium, right? But we have absolutely nothing at equilibrium except for the Kc value. So what I'm going to do is the following, okay? I'm going to just make an assumption quickly, and I'm going to show you how I'm going to tackle this question. So I'm going to say, well, suppose we say that we used an X amount of hydrogen iodide, okay? Or if you want to, just to make it easier for yourself, you can say, well, what if we used an amount of hydrogen iodide of 2x? So the reason why I'm saying 2x is so that it's easier to use that ratio there. And please, ladies and gents, remember that we only use the ratio on this part here that says change. You do not use ratio and proportion on any part in this table except in that change part. So what if I say to you, well, we produced an X amount of hydrogen. So if we produce an X amount of hydrogen, so for every one, there's one here. So for every 1 mole of hydrogen, I use 1 mole of, I produce rather 1 mole of iodine. So for any amount of hydrogen that I produce, I will produce the same amount of iodine. So if that is X, that will also be X. So this one says, okay, for any amount of hydrogen that I produced, I would have used twice the amount of hydrogen iodide. So in this case, if I produce X, how much would I have used here? It would have been 2X. So it's according to those ratios over there, right? So this tells me, okay, I started with 0.5 and I use 2x. What do I have at the end? Of course, I will have 0.5, okay, minus 2x. And then this one, I started with nothing. I produce an x amount. So remember, when you produce something, okay, it means that you have, you add to that. So I started with nothing. I add x. I'm going to actually produce this amount. So at the end, I've got what? X amount of hydrogen. As well as this one, I started with nothing, produce X amount. At the end, I've got an X amount of hydrogen, of iodine, right? So now we get to the last portion and say, well, what if we say our concentration there? So remember, concentration is number of moles over volume, isn't it? Okay, so I'm going to say, well, that's going to be concentration is number of moles divided by volume. So number of moles is that guy there divided by volume. Remember, volume is 0.5. So it means that we've got 0.5 minus 2x, number of moles divided by volume, which is 0.5. Okay, and the same is true for this one, number of moles divided by volume. We've got x over 0.5, and then the same is true for that one. That's x divided by 0.5. Okay, now keep in mind they had given us the Kc value. All right, so please remember that we know they said to us calculate the number of moles of iodine, okay, present at the 6 minute, that is at equilibrium, right? So we actually want the number of moles of iodine, and in fact it would have made sense to make that x. So it means that we would have produced x, produced 2x amount. Okay, right, so now we're going to say, all right, so let's find out our Kc expression So please remember, when you write down the Kc expression, it's the molar concentration of your products. Okay, and please remember, these are all in gaseous phase. Okay, so that's gas, gas, and gas. Okay, so it's the molar concentration of your products. Now please remember, ladies and gents, in your Kc expression, we only include substances that are in gaseous phase as well as in aqueous phase. So anything that is solid or that is liquid, you do not include in your equilibrium expression. Okay, so in this case, I'm going to say, well, what are my products? It's going to be hydrogen iodide, hydrogen rather. Those are my products. So that's hydrogen. Molar concentration of my other product, which is iodine. Okay, divided by, now obviously this is to the power 1 because the coefficients are 1 there, divided by hydrogen iodide. I'm going to include it because it's a gas, so that's hydrogen iodide. Okay, but remember the coefficient is 2, so in this case, remember the coefficient becomes the power over there, right? Now we were given the Kc value to be 0.04. Okay, we're just going to do some mathematical gymnastics here. Okay, so let's now substitute. So we've got that x over 0.5. By the way, this is sort of x divided by 1 over 2. So if I say x divided by 1 over 2, this is the same as actually saying 2x, because x over 1 divided by 1 over 2, remember, I can just simply say x over 1 and I convert the division into multiplication. But remember, once I change that to multiplication, I need to invert. So that's the same as 2 over 1 there, right? So this would be the same as 2x. Okay, I don't want to complicate your lives. Okay, so in this case, that's x over 0.5, which is the same as 2x. So that means this is 2x, okay, multiplied by another 2x divided by, now please, I want you to note, in this case, you've got 0.5 minus 2x over 0.5, or you can just simply say, well, 0.5 divided by 0.5, that's 1, and 2 divided by 0.5, okay, that would be 4. So this would be the same as 1 minus 4x, okay? So that would be 1 minus 4x, but remember, this is squared, okay? Right, so so at the top there, what do you have? You've got 2x, and I want to show you something there. So that you've got 2x squared divided by 1 minus 4x, okay, all squared. Okay, my black marker kind of wants to give up on us, okay, which is equal to 0.04. Okay, so look at this. What we can simply do is just take the square root on both sides, right? Because you would actually be able to get rid of that square there. So I can take the square root, but remember, what I do on the left, I do on the right, isn't it? Okay, right, and I don't necessarily need to bother myself with that plus or minus, because in this case, obviously, we can never have a negative equilibrium constant, isn't it? So in this case, what do I now have? It means I'll have 2x over 1 minus 4x. Remember, the square root would sort of cancel those squares there, okay? And what would be the square root of 0.04? I believe you would get 0.2 over there, right? So all I need to do is just cross multiply, okay? So 2x times 1, that's 2x, which is equal to 0.2 into 1 minus 4x, okay? So we can divide by 0.2, okay? And by the way, the physics is up now. All that we are doing is just the maths now, okay? Right, so in this case, we're going to say 2 divided by 0.2, Okay, so that's the same as just multiplying that by 10. Okay, so 2 divided by 0.2, okay, that will give us 10. Okay, so that would be 10x there, which is equal to 1 minus 4x. I'm sure by now you should be able to see your way around this. So I take this to the other side, it now becomes 14x. Okay, if I take that there, which is equal to 1, okay, I can divide both sides by 14. And please just help me out just to verify if what I've done is correct. Okay, and our final value is, okay, I get 0.071. Okay, so remember x, we represented that as the number of moles at equilibrium. Okay, so as a result, that would be moles. So this would be the number of iodine, okay, moles at equilibrium, which is what they had initially asked us to calculate, right? So that is how we are going to tackle that question. I know it looks like a nightmare, but in this case, please just remember that all we simply did was just to follow the normal standard process of how to use that ice table. Okay, the only difference here is that instead of having values over there where we would use ratio and proportion, we now had x. Okay, so started with nothing, we formed x amount there. Okay, and in this case it means we had x, so that's 1 is to 1, so x is to x. 1 is to 2, so x is to 2x. And in this case, all we simply did was just follow the process in terms of getting those values at the end. So ladies and gents, I hope that you enjoyed that question. Okay, and it will help you in your preparation for the exam. By the way, please don't forget to subscribe for those of you that haven't, and we'll just continue flooding you with those questions, okay, just to help you prepare for your exam. All right, and I'll see you guys again next time. Itada.